Welcome to the lesson, Types of Fuel Cells, Operating Principles, and Chemical Reactions. In this lesson, we will discuss how different types of fuel cells operate, the specific ions that move through each type of electrolyte, and the chemical reactions that generate electricity. Let's look at our lesson objectives. By the end of this lesson, you will be able to identify the different types of fuel cells. Next, you will be able to distinguish between the high temperature and low temperature fuel cells. Following that, you will be able to explain the operating principle of each type of fuel cell. Finally, you will be able to describe the basic chemical reaction that occurs in each type of fuel cell. What is the function of a fuel cell? A fuel cell is a device that generates electricity by combining hydrogen and oxygen through a chemical reaction. It does not burn fuel. Instead, the reaction releases electrical energy that can power devices. As long as the system provides hydrogen and oxygen, the fuel cell can continue to generate electricity. Why are there different types of fuel cells? Fuel cells come in various types because they use different electrolytes. The electrolyte is the part of the fuel cell that allows specific ions to move between the electrodes. The type of electrolyte determines how the fuel cell operates, including its operating temperature and what fuels it can use. The different types of fuel cells, categorized by their specific electrolyte materials and operating temperatures, are molten carbonate, solid oxide, alkaline, phosphoric acid, proton exchange membrane, or solid polymer, or PEM, and direct methanol, PEM. The high-temperature fuel cells are molten carbonate and solid oxide, and the low-temperature fuel cells are alkaline, phosphoric acid, proton exchange membrane, and direct methanol, PEM. Fuel cells can be categorized by their operating temperature. High-temperature fuel cells operate at very high temperatures, enabling them to utilize a broader range of fuels. However, they take longer to warm up and pose greater management challenges. Low-temperature fuel cells operate at a lower temperature, which allows them to start quickly and makes them easier to control. However, they typically require cleaner fuel. Molten carbonate fuel cells operate by moving carbonate ions through a liquid carbonate material that serves as the electrolyte. These ions travel from the cathode side of the cell to the anode side. These fuel cells operate at high temperatures, requiring approximately 1,200 degrees Fahrenheit, 650 degrees Celsius. During operation, hydrogen reacts with carbonate ions and oxygen. This reaction produces water and carbon dioxide as byproducts while generating electricity. Each molten carbonate fuel cell creates between 0.7 and 1.0 volts of direct current power. Solid oxide fuel cells operate by transporting oxygen ions through a specialized ceramic electrolyte. Oxygen ions travel from one side of the cell, the cathode, to the other, the anode. These fuel cells require extremely high temperatures to function properly, operating at around 1,830 degrees Fahrenheit, 1,000 degrees Celsius. Inside the cell, a chemical reaction occurs where hydrogen or carbon monoxide combines with oxygen ions. This reaction produces water or carbon dioxide as byproducts and generates electricity simultaneously. Each fuel cell generates a small amount of electricity, typically between 0.8 and 1.0 volts of direct current. In alkaline fuel cells, hydroxyl ions move through an alkaline electrolyte from the cathode to the anode. This movement enables electrons to flow through a circuit, generating electricity. These fuel cells operate at low temperature, typically between 150 to 430 degrees Fahrenheit, 65 to 220 degrees Celsius. During the chemical reaction, hydrogen reacts with hydroxide ions to form water, releasing electrical energy. Each cell produces 1.1-1.2 volts of direct current. In phosphoric acid fuel cells, hydrogen ions move through a liquid phosphoric acid electrolyte, while electrons travel through an external circuit to generate electricity. These fuel cells operate at low temperature, typically between 300 to 400 degrees Fahrenheit, 150 to 205 degrees Celsius. During the chemical reaction, hydrogen reacts with oxygen to form water and generate electricity. Each cell produces approximately 1.1 volts of direct current. In proton exchange membrane fuel cells, hydrogen ions move through a solid polymer membrane, while electrons flow through an external circuit to generate electricity. These fuel cells operate at low temperature, typically between 160 to 195 degrees Fahrenheit, 70 to 90 degrees Celsius. During the chemical reaction, hydrogen reacts with oxygen to form water, releasing electrical energy. Each cell produces approximately 1.1 volts of direct current. Engineers consider PEM fuel cells the most promising type for automotive use because they meet many vehicle requirements, such as quick startup and efficient operation. Most fuel cell vehicle prototypes built to date use PEM fuel cells, as this technology has been widely tested and developed. Direct methanol. Fuel cells use liquid methanol directly as their fuel. Hydrogen ions move through the membrane while electrons flow to generate electricity. These fuel cells operate at low temperatures, typically 266 degrees Fahrenheit, 130 degrees Celsius. The chemical reaction produces carbon dioxide and water, generating electrical energy. Solid acid fuel cells, SAFCs, are a type of fuel cell that uses a solid acid electrolyte rather than a liquid or polymer membrane. They operate at medium temperatures, usually between 150 and 250 degrees Celsius, 300 to 480 degrees Fahrenheit, which is higher than those of low-temperature fuel cells, such as PEM fuel cells. Each SAFC can produce a voltage slightly above 1 volt when not connected to a circuit, like other hydrogen-oxygen fuel cells. Because the electrolyte is a solid acid that carries protons, these cells do not need liquid water inside or special humidifiers. Still, they must stay within specific temperature and gas ranges to prevent the electrolyte from breaking down. Researchers are still improving solid acid fuel cells, SAFCs, in the lab, and challenges such as sulfur damage, material weakening at high temperatures, and poor performance in very wet conditions have slowed their progress toward low-cost, widely available products. Let's look at the summary for our lesson, Types of Fuel Cells, Operating Principles, and Chemical Reactions. Fuel cells generate electricity by combining hydrogen and oxygen in a chemical reaction instead of burning fuel. They continue to produce electricity as long as they receive hydrogen and oxygen. The main types of fuel cells include molten carbonate, solid oxide, alkaline, phosphoric acid, proton exchange membrane, and direct methanol. We group fuel cells into two main temperature categories. High-temperature fuel cells, such as molten carbonate and solid oxide fuel cells, operate at very high temperatures. These fuel cells can use a broader range of fuels, but they take longer to warm up. Low-temperature fuel cells, including alkaline, phosphoric acid, proton exchange membrane, and direct methanol fuel cells, operate at lower temperatures. They start up quickly but usually require cleaner fuel. Each type of fuel cell generates electricity by moving specific ions through its electrolyte while electrons flow through an external circuit. Different fuel cells operate at different temperatures and produce different voltage levels. Engineers consider proton exchange membrane fuel cells the most promising option for vehicle applications because they meet key requirements such as fast startup and efficient operation. As a result, manufacturers have built most fuel cell vehicles using this type of fuel cell. Thank you.